Welcome, everyone. My name is Patrick Godau.
And I'm Piotr Kalinowski.
And here is why you should take prevalence shifts seriously in model deployment. When researchers talk about domain shifts, they typically refer to shifts between the train and the test set. However, what about shifts that happen dynamically when the trained algorithm is deployed? Specifically, how to select and deploy a model when disease prevalence changes over time or differs from country to country, like we've all seen happen during the pandemic. Prevalence shifts first came to our attention in the context of metric selection. Let's consider a hypothetical COVID classification model, which was trained and tested on a balanced dataset. Afterwards, the algorithm is deployed in the wild, say at a time and location where the prevalence is 1%. The very same algorithm now yields completely different metric values. In the following, let's assume that we have a decent estimate of the prevalences our model will face. This estimate can be based on literature, experience, or even be derived data-driven on the fly, as shown in prior work. Ideally, we would like to have a metric into which we can plug these class prevalences to estimate the model performance. And here you go. There is a metric which has so far been overlooked in our community, expected cost. Expected cost can be viewed as a generalization of accuracy and its inverse, the error rate. They rely on summing over a subset of entries within the confusion matrix and dividing by the number of samples. Expected cost does the same. It sums over all entries, but it allows a cost factor to modify the weighing of each confusion possibility. By rephrasing, expected cost can be written with explicit prevalence factors. Now, and this is important, if we replace the test set prevalences here with the deployment ones, we obtain a prevalence adjusted metric. Coming back to our example from before, we see that in this case, the value of expected cost with adjusted prevalences remains the same under the prevalence shift. So the metric enables the comparability of performance values across datasets with different prevalences. Okay, does this mean the issue of prevalence shifts is now solved?
Well, the devil's in the details. There is an important design choice that we ignored in the explanation so far. How do we convert the softmax output of a neural network into an entry in the confusion matrix? Well, according to our research, the most widely used method is the argmax operator. So let's investigate it in detail. To draw broad conclusions, we gathered a variety of medical image classification tasks of different modalities. For each of those, we simulated different deployment settings, varying the imbalance ratio, namely the ratio of the most frequent and the minority class. Let's see what happens applying argmax in these cases. In this plot, the x-axis shows the imbalance ratio of the deployment dataset. We plot against it the difference of metrics value when the predictions were made using argmax and using optimal decision rule found using grid search. We can see that for all metrics, the difference from optimal performance increases with change in imbalance ratio. So what's going on? Well, we know from Bayes theory that argmax is only the optimal decision rule for accuracy when scores are calibrated. And they're not. The higher the prevalence shift, the worse the calibration gets. In other words, predicted class scores reflect statistical accuracy less and less. So how do we fix this? The most popular way of recalibrating a model is performing temperature scaling. But does it solve our problem? Not at all. Not even if we perform recalibration by using the known prevalences of the deployment data. Why is it so? This is because temperature scaling does not include enough parameters. All logits are scaled by the same scalar t. What we need is an additional bias vector b, making the recalibration non-accuracy preserving. In other words, a recalibration that can change the predicted class. And it works. After prevalence shift adjusted a fine recalibration, the calibration error remains low with varying imbalance ratio. For expected cost and accuracy, argmax is the optimal decision rule now. Note that this does not hold for all metrics. This confirms what we know from Bayes theory. argmax is not the optimal decision rule in general. Let's discuss all the exciting details at the poster, and keep in mind the simple take-home message. Prevalences matter a lot.
not only during training.